Well, good afternoon, good morning, and good evening to those that have joined us for the RDI webinar. This is part 2 of our Modal Amplified new product introduction. Today, we do have a special guest with us, and we will be introducing and talking to Jeff Hay, the CEO at RDI Technologies, in just a moment. Thank you again all for joining us. Give us a couple seconds and we'll get started. Well, good day to everyone as we join the RDI Technologies webinar. Today, we're going to be talking about Modal Amplified, a new product that we introduced a few weeks ago. Today is part 2. We're going to go through part 1 just real quick so that we can get everybody up to speed. Thank you again as we still have attendees filing in. Just sit back, get your drinks, relax, and be ready in a few seconds. Good day again, and welcome to RDI Part 2 of Modal Amplified webinars. Today we have a special guest with us, and Dr. Jeff Hay will be going through what we did in Part 1. So we have a few more. It seems like everybody's pretty on time today, guys. We have it's kind of slowed down a little bit. So just give us probably about 20 more seconds. All right. Again, good day to all and welcome to part 2 of Modal Amplified. Please feel free to ask your questions as we go along throughout in the section marked Q&A in Zoom. And now, Jeff and Luca, welcome and let the floor begin.
Thanks, Don. Today, as Don mentioned, we're doing our second webinar on Modal Amplified, our new product that leverages a camera to do modal analysis. And so the first part was an introduction. You can find that on our website, and I'll show you where in a second. But today we're doing part 2, which is accelerating your time to insights. And, you know, that's sort of a key part of what this product is about, really about accelerating your time to more information about your product or your design or your asset. And so today I'm with Luca Del Nero, Managing Director at Darkwave Thermo. And so we're really excited to have Luca here, who has a background in modal and experienced, you know, in not only motion amplification, but a whole host of technologies. And so we'll do some real quick introductions. Again, my name's Jeff Hay. I'm the CEO of RDI Technologies. My background is in physics. So I started in optical physics, always had an interest in photography. You know, my original research was in astronomy, but using cameras in astronomy and high-speed cameras, which is not very common, doing a technique called lucky imaging, where you would try to get lucky and get a good image of a star by taking lots of pictures of a star. So that research was really first started in really fundamental R&D. but then it became applied, applied research, focusing on the atmosphere, the dynamics in the atmosphere, and modeling it through cameras, and then also structural health for example, bridges and critical infrastructure. And so that led to the original underpinnings of the technology that we use today at RDI. And which is where motion amplification came from. So there's a little bit about me. I'll let Luca jump in and give you a little bit of background on himself.
Hello, everybody. As Jeff said, thank you. It's a pleasure to be here. My name is Luca Del Nero, and I started many years ago when I have long blonde hair as a reliability engineer, starting with tomography and covering almost all type of diagnostic technologies in condition monitoring. So about 13 years ago, I decided to start our company, at the beginning with tomography. And then in 2018, I saw this new light of motion amplification that completely changed our approach to the inspection. Okay. If before motion amplification, we were using our vibration analyzers, infrared cameras to detect what's going on. After that moment, today we see, okay, let's see what is visible, and then we will decide what to do. So thank you so much for being here.
So thanks, Luca. And just a little bit of housekeeping before we start. I had mentioned earlier that this is the second part of a webinar. The first part, was done 2 weeks ago on the sort of the technical aspects of and how the modal amplified product works. So this is a snapshot of our website, but I'm actually going to bring up a browser and just kind of show that here. So you can see here's our website. If you go over here to resources, you can go down to webinars, and then you'll see where our upcoming webinars are. So you can see that, here's our modal amplified. You can see what our next webinar is. Here, you can go ahead and register for it. And then you can also scroll down and see that you've got a whole host of previous webinars on the website. So you can sign up and watch those. The first modal webinar will appear here, and you would be able to go back and watch our part one. So just kind of giving you a little bit of info on where you can go to learn more about the modal amplified product, or just actually learn more about other products or other case studies. There's a whole host of webinars here that you can sign up for. And then, of course, this webinar will also, you'll get a link to be able to watch this webinar as well. So we are recording this. Also note that there's, our presentations are always very video heavy. And so depending on your download connection, really determines how well you view those videos. So not everybody will see them the same. Just know that they're playing fluid on our end. And then when we go to record and put them in the cloud and you watch the webinar that from the cloud, they will be smooth on that playback. So if a video doesn't play back very smooth, rest assured you can go on and watch the webinar on the web at a later date and see that. Also, Dawn mentioned ask lots of questions. You can put your questions up in the Zoom, and they will be answered, the best we can. Last week we got a large amount of questions, and we followed up with everybody. We'll do the same this time if we get too many. But also Dawn will jump in at different times during the webinar and ask those. So go ahead and put those questions, into the chat in their Q&A section, so that we have them there to ask as we go. And then also another thing that would be really good is to sign up for the webinar, or sign up for our newsletter. So, if you go to the website, you can show this again, the website here, you can go to the contact. And if you click that, there's a place to sign up for the newsletter. It's at the bottom of each page. So that's another good way to stay up to date on all things motion amplification and RDI. Okay, so let's get into the webinar. So what we're going to cover today a brief overview of motion amplification. Inevitably, we always get sort of new people to the technology, and it's really important to understand the motion amplification part to see how we're leveraging that with modal amplified. And then we'll talk about modal amplified. We'll go in an overview. We'll talk about some of the technical features. I'll give some background. And then Luke and I will have a short discussion on, modal new versus old, and, what the kind of setting the stage for the case studies that we're going to show today, which are a little different than last week's. We try to show very classic examples. Today, we're going to try to show specific examples that you would find in a facility or in a product design company, where it's creating product and doing modal testing. Okay, so what is motion amplification? Let me just kind of dive in, and I'll go through this pretty quickly so we can get to the modal amplified. Essentially, we're using a camera to turn it into a vibration sensor, but instead of just a single point vibration sensor, you can think of a camera, you can think of the pixel as being the vibration sensor. And so now, instead of having millions of pixels, you have millions of vibration sensors. And if you think of it that way, now a single modest HD camera has millions and millions of vibration sensors across the entire field of view, continuously blanking the field of view. And now we can measure at every single point in the image and make the motion bigger to the eye so that you can see it. And once you can see it, you can do a lot of interesting things with it. It becomes a very powerful tool when you can visualize the motion. So this is a car engine. If anybody's popped the hood of a car, they know they're not going to see this. Hopefully, they're not going to see this in their car. But when you use motion amplification, you can clearly see all of the moving parts that are moving, and you can actually filter for individual frequencies as well. Here's the xylophone. This is at around 1300 hertz. So really, you can do it at any frequency. You just need to use a camera that's fast enough in terms of the frame rate. And then here's a wine glass. So I'm just trying to show very classic examples of things that we all know vibrate. This is just simply dinging the wine glass with a spoon, and then you hear that ring. This is actually what that ring was being created, what's creating that ring when it vibrates. This is 786 hertz. But this is something I think more applicable to a lot of people in the maintenance world, where they want to see what an asset's doing. And, even with modal, as with just condition monitoring, current state of the art would be placing a contact sensor on it and trying to determine everything about that asset from either a single point or a very sparsely set of sensors on an asset. So you're missing a lot of information, and sometimes context is key to understanding the asset. So there you can just see that it's lifting up and down. And then, of course, we can do things like transient, where you can measure things that are moving through the field of view, because, again, we have full field vibration. And then this is showing the vibration, and this is the way that it's moving through space. This is the dynamic vibration that's occurring as it moves. And then this is the frequency spectrum of the moving object. So you can actually get spectrum of moving objects with this technology as well. But the idea here is that, you take something complex, and this is, again, going to translate to modal, a pretty complex and sophisticated data collection process. And you take that and you really transition that to something simple and visual. So, it's one thing to look at this spectrum and try to understand what's going on, but you can simply look at the video and see one side's moving up while the other side is moving down, and you can see it's out of phase. And also the scaling, and again, just to kind of translate this with modal, if the more sensors that you put on something, if a few dozen sensors with contact is pretty comprehensive data collection, pretty cumbersome, can be expensive and difficult to manage. So, with motion amplification in a camera, and certainly with modal amplified, now you can scale up your data collection, and you don't have to worry about your grid for modal and kind of a sparse grid. You have the entire asset blanketed, and we'll show those examples. So some of the technical details, we're measuring displacement, There's no processing time. You can do this live. You can see down to less than a micron, nanometer, hundreds of nanometers level motion. Do it in three dimensions as well. So just some of the details around it. We're not going to go into all of these today, but that's just a little bit about motion amplification and the camera capability. But the key thing here is that you can measure large field of view very quickly. You can place virtual sensors basically anywhere in the scene, and that's what allows you to really do a comprehensive data collection. And the speed to actionable information is really key here. If you've ever done Modal, it takes a little bit of setup and time, but with a camera, you're sort of already have all your sensors right there on the asset. So really what we're doing is, we're taking what used to be a time-intensive and complex process, and we're really trying to simplify that with a camera. So you can think about if you followed the motion amplification progression, you can think about what motion amplification has kind of done for ODS, in that we get the information that you need to make the same decisions that you would do with ODS in a much quicker manner, in a much easier manner. We're doing that. You can think of that analogy as the same with modal amplified to traditional modal analysis, where we're really trying to get the results that you need to make the decision to allow you to move to the next process of whatever it is you're trying to accomplish. And so you can imagine that's done by having these millions of virtual sensors, pixels of a camera blanketed across a asset that you can now turn into your sensors for modal analysis. And you can get the results immediately, and we'll show that workflow. Okay, so you can do this, there's the 3D camera just sort of pointing that out. But that's what it looks like. It's just a really small Pelican case box that the hammer plugs into, and then the camera plugs into, and then you get the synchronization. You can plug in a reference Excel as well, and then you can also put a shaker output, hook up a shaker and control the shaker as well. So it's all, the whole idea is a one-stop shop. You get what you need all in one sort of package, so that you don't need extra pieces or parts, right? And you do this all really, really simply and really self-contained. Okay, so there's a couple plots from the software, but we're leveraging the fact that now we can synchronize this hammer and this camera, and to the point where now we have coherence between the two, and we can get FRFs, and we can get proper structural properties, and then do this with high speed. We've got some high speed examples today. And really eliminate the need to recapture data. You can even take, if you change your mind and you've already done the acquisition, you can, after the fact, add virtual sensors to a location and get new data from that location, which is pretty powerful. If you decide you need to measure somewhere else, you don't have to redo a modal test. Okay, so let me talk, here's a few of the technical details. And then Luke and I are going to talk a little just about modal in general, but it can be used with any IEPE impact hammer. It does integrate the reference Excel 24-bit ADC, and you can export the waveform spectrum coherence, the FRF, all that data to UFF files. So if you want to import this into, a finite element package or some other piece of software where you want to design or change something, you can easily do that. Basically, unlimited virtual displacement sensors. You could just draw those boxes to the heart's content and measure as many places you want. We do include a stability diagram and automatic mode shape detection. Again, the idea here is for you to take this video data, immediately process it, and immediately have a visualization of your mode shapes within minutes, right? And so all of this is there. We'll demonstrate this. Coherence map, that's something that's new. But if you've seen our motion map, it shows where the most motion is occurring. This is also showing coherence across the entire field of view. So you can get an idea of what's coherent in a nice visual. And then the shaker input will allow sine sweep, chirp, broadband noise, and then a user-defined file. So if you want to put your own defined waveform into the shaker, you can do that all in the software here. Everything can be done in 3D, and it is compatible with our high-speed MX camera. And then there's a few modes: impact, operation, or shaker mode. So just wanted to go through a few of the details so you know exactly what's there and how it can be leveraged. So at this point, I want to kind of break out of sort of the background and just have a short little conversation with Luca, who has a background doing modal analysis, and just kind of talk a little bit about that. So Luca, one of the things that in the past, we're kind of changing the way modal analysis is done. Maybe can you talk a little bit, like before you could use a camera, how would you set up a modal experiment? What would be the process?
Yeah, just for the audience, we are covering the market of Italy and Switzerland, and we work with any type of industry. Okay, in Italy, the industries are almost of every kind apart mining. We don't have larger mining. So we work for automotive, energy, nuclear. We work for household appliances, and typically the situation was to set up standard systems with several accelerometers and multiple bump tests for development of new supports, new components, or to solve existing problems. So, for example, going in the field, for example, in power production plants or refineries, trying, for example, to figure out which could be the model shape or the behavior of any support and why that support went in resonance and failed. So we try to develop new concepts and using modal analysis or shake with bump tests or shaker tests and following finite element calculations. The goal was to create new and more reliable parts. But this take a lot of time, because if you're in the field, you need to find a way to bump in the right way, and maybe your components is stainless steel. And so the problem is, how can I fix the accelerometer? Or if it is a small support, the support is so small compared to the accelerometer that you have, that start to be quite tricky to do a bump test. Okay, and then when you are on the shaker, maybe you don't know if the resonance that you find is really related to your component, or maybe the fixture, or maybe a wrong screw that you set up on the shaker and the screw is not rigid enough. Okay, and moving to motion amplification, this became totally different. So you can do a shaker test and discover that maybe your first natural frequency is not related to your component, but simply to the fact that the fixture, the connection to the shaker must be done with two or three more screws. Okay, and this is something that happened. Or you can clearly see during a bump test that you're bumping on a node or on an anti-node, and so you don't know if you immediately know where is the right point to put your accelerometer, or where not to put your accelerometer. Or if it's stainless steel, you don't need the accelerometer, because you just can go directly with the camera. And so you don't need to find a way to find glue, and maybe it's not allowed to glue anything on your pipe. Or when you develop, for example, small parts, we've done a test a couple of years ago on a micro component for a satellite in a Swiss university, and the problem was to define a resonant frequency and the mode of something that was less than half an inch of diameter. And in that case, there was no physical way to put an accelerometer. And today, this type of application can be done with a camera alone. So this is our this is our experience and the great advantages that we found using the camera.
Yeah, I think you're good. I think your example of the fixture is a really good point. We've seen where motion amplification, and certainly with the Modal amplified, has revealed that the automotive manufacturer might have for a part might have a specification that the vibration has to stay under, and it turned out that it was the fixture that was causing it to go out of spec. So just by tightening the fixture, they were able to bring the tolerance of their part within spec. So the component itself was in spec the entire time. It was the fixture itself that was bringing it out of spec. And so that sort of insight is pretty powerful. Okay, so I'm gonna let you take the screen, Luca, and then you can kind of go through some of your examples that you have.
I go through a couple of examples. I will switch off your screen, Jeff. Okay. Just a couple of quick examples. One is related to a very simple bump test on the door of my car. The reason is very simple. We receive sometimes requests of support from automotive companies or tractor design, and the door is something that normally vibrates. Okay, and because almost 90% of our application are restricted under a non-disclosure agreement, so we need to create something for the audience that can show what is possible with the system. So here you see, for example, my bump test done on the car. The light is not perfect because I was in my garage. So with a bump test, you can immediately see, okay, was a little bit of light because there was some AC light here. Okay, so you see me bumping my door. I will launch it again. So this is done without any second accelerometer, just bumping. Okay. As I said, we can see the waveform of everything, of the hammer, of any measurement point. So we can see how the system has performed. We can see the spectrum for all the components. We can see the frequency response function in any point. Okay. And as I've said, we have a stability diagram where, depending on some settings that we can adjust the minimum, maximum frequency, the order for the calculation, all tolerances, we can define which mode of vibration are stable in frequency and damping, and so that can be considered that good enough. We can play with everything here. So in this case, the system has decided that there are two main frequencies. One is flexional, the other is torsional. And we can use the vectors to easily represent how this is done, okay? And like a normal motion amplification, we can see how the door is moving. In this case, it is moving at about 15 Hertz up and down, clearly visible. And we can see the second mode of vibration. In this case, there is a torsion on the support. I make it a little bit bigger. And in this case, you can clearly see how the system works. Again, this was done very quickly. Open the door, put a couple of magnets. In this case, the markers are just magnetic, but you can paint, you can use anything. You can use a screw, you can use the sticker here. Everything can be done. We can calculate immediately, for example, what happens here. If I go in my stability, and I put one more spot here, and the system can automatically analyze. The distance was different from 1 meter, but the system can immediately analyze. I have too many screens now here. Yeah. And again, I have the calculation and the motion on my door in the second point. So every single point for sure not where it's completely white, because there is no optical contrast, so the system is unable to calculate where there is no optical contrast, but every place where you have any contrast. So if this point was not the right one, you can immediately go to the second one or go in any other place where you want to see the motion. Another simple test that I have done, again for the automotive market, is related to the motion of the panel of the door. In that case, I must wash my car more frequently, by the way. So this is the typical bump test that is one of the requests that we receive sometimes is, we are producing tractors and all the panels around, or some bulldozer, all the panels around are shaking, and we want to see if the calculation of vibrational modes are correct, or why we have a vibration at this frequency that is not expected. Okay, and so in this case, we see again what can be visible with our bump test. So we can immediately see the motion of the door. And again, for every single point, we can go to see all the parameters. And again, we have a stability diagram where there are some suggested frequencies for our modes, okay, for every single point. So the system itself gives us immediately what is a suggested mode and what is a mode that could be, but it's not exactly what we expect as a good mode, very stable. Okay, and the system automatically make the calculation for us and suggest and create video where we can immediately see what's going on there. So again, we go in our door at the first frequency, that is about 45 Hertz, and you see the door is going left to right as a single part here. And if you go a little bit higher, you can clearly see that the door has a totally different behavior. Okay, the two parts are, there is a torsional motion, and the red spot is almost stable, it's not moving there. While if we look at the other frequency here, that's about 63.2 Hertz, we need to increase a little bit the amplification. We see a similar motion, but this time the red area is moving more than before, while the blue one is moving less. The good stuff of this module here, that everything that has been filtered and analyzed by the software and the system can be afterward analyzed with the standard motion amplification tool, so we can add more annotation, charts, and phase map. And I'm sure that Jeff will have something very interesting where the phase map can be very impressive. And to do a test like this was very easy. You see, just 3 stickers, a couple of lamps. All the neighborhood were looking at me like a crazy guy bumping a car. But no strange setup is required, no accelerometer, no computer there, just a portable laptop and nothing more than that. And if you don't like the position, you can simply change the position of those stickers, put more, no cable, no glue is involved, no magnet, no additional mass. So in this case, the real dynamic of the system can be respected. You cannot change, you don't take any risk to change any dynamic aspects of your system. In some cases, when you inspect very small parts, typically some support of a washing machine, if you stick an accelerometer on a support of a washing machine, sometimes of a pump or on a pipe, sometimes the accelerometers can be even bigger than support itself. Today, there are very small accelerometers, but the mass of a support is in any case very small, or a coffee machine. So in this type of application, the use of an optical camera is for sure an incredible advantage. And in general, for any type of application, even if it's big or medium size, everything can be done very, very, very quickly without the need of any wire flying around or a wrong position, do the test, and maybe go to the computer, make the simulation and go back because the data are not exactly what you want. I did 10 tests here just to set and to see the behavior of the door, and just changing the position of my stickers just to see quickly which is the best position to see the motion. Okay, and this is the great advantage.
I'm on mute. Thanks, Luca. Yeah, I think that the speed, just kind of idea, how long that took for you to do that. How long would it have taken you if you would have done it, say, with traditional sort of accelerometers?
Traditional accelerometer for something like that would have taken probably the setup 1 hour, then take the data, download the data, put in the computer, try to see how the motion works. Okay, probably one morning. Yeah,
and then I'm thinking that just took probably less than an hour to do that. 30 minutes, less than an hour.
Oh, it took more time to install the system and find a plug for the electrical power and move the car in a quiet location.
That's the longest part.
And say, oh, where is my lamp? Generally, it took probably 5 minutes.
Yeah, and you can just go through rapid testing, and I think that's the key too. Is that the idea is to again get you to the data that you need so you can move on. I think we find that we do very comprehensive tests for a very small amount of 1 or 2 pieces of information.
Jeff, from my point of view, the biggest advantage of this technology applied to not only to model analysis, but to everything, is it stops any discussion. Okay, so imagine that you've made your finite element model, okay, and you bump it, and maybe the frequencies are similar or there is something that is different. You start with long discussions. Okay, here you bump it and you see it. Okay, if it as expected, you're good to go. If it's different, for sure it cannot be the reality. The model must be wrong, because this is reality.
Right.
So when you see it, everybody, I remember we did that shaker test, okay, and everybody saw the screw bending and said, okay, this is the problem. Stop it. We don't need any calculation. We don't need to put the system, the model into a computer and see what's wrong. You see it, you fix it, and you're good to go very quickly.
Yeah, I mean, I think that's a very good point. This is actually really what it's doing. I mean, this is the real object you're seeing on the screen, the actual object. Speaking of objects, I've got a data set here I was going to share.
Can I just
go for it.
I have a couple questions, and I think now might be the time. So thank you, Luca. That was very interesting. So the first question is, instead of a physical reference accelerometer, can I designate an ROI as the reference alongside an IEPE hammer to get the appropriate transmissibility FRF?
Yeah, sure. So you can put a reference Excel on it to, so you get that. That's a good question. Let me get back with him on that. I'm not 100% sure about that. I don't have the answer right offhand. I don't know, Luca, if you know, but I can definitely talk to one of our team members and then find that out, and we'll get that question back to them. But that's the sort of thing that we like those questions, because if we don't have that built in, we'd love to be able to add that feature if our users feel like they could use that.
Yeah,
it's a part of the question. Can you repeat it, please?
They want to know if you can, instead of the reference Excel, they want to know if you can assign one of the ROIs as the reference.
I don't think so at the moment.
Yeah, I'm thinking not, but often I don't always know all the answers. So we'll see. We'll see what they say, but we'll note that too on as a potential add, if not. Okay.
And that's the value of these questions, like Jeff said. So ask them, and like we said, if we don't know, we'll get back to you and get you that answer. So another question is, what's the specific equipment needed for a modal test with this technology? In the previous session, Jeff said that the accelerometer was not necessary. So, and where is it connecting this equipment, the hammer, the accelerometer? I guess just, I don't see, do you have the box there, Jeff?
Yeah, I can. I'll share my screen here, and I don't have the box here, but I'll get a. It's in a different room, but let me share my screen here, and I will bring up this window here. So this is what it looks like. I mean, that's maybe a foot wide, here, just give you an idea, maybe a little less. So the whole kit comes with a hammer, comes with this box, the camera. You don't need Excels. You can use a reference Excel, but you don't have to. But the bigger thing with not needing Excels is you don't need any acceleration, any accelerometers on the object for your measurements. Those are all done with the camera. So so you only need Excel if you want a reference accelerometer to be used. You do not have to. You can certainly do the do it without it. It's just whether or not you want that reference Excel for that measurement. But it's not required. You can certainly do it without that connection put in.
Okay, you guys are caught up for now. Thank you.
Okay. So let me show you this example, and then Luca, feel free to jump in if you've got any comments. But I can kind of show you through. We have these videos, and then we can do an unfiltered, and we can kind of show. You can see the hammer here, just giving you an idea of the impact, and then how the measurement was made. And so that's the measurement for this is on a bicycle. This is the brake. The disc there, and then so again, this is just a really fast setup. You record video, you acquire your video, you draw your boxes, and you're immediately to the stability. Diagram. Now we did this with an MX high speed. You can see the frequency range out here to the 600 plus range, and then we're immediately into the analyze. And we can go through and actually see these mode shapes on this disc, on this, cycle it, ramp it up a little higher. And so immediately you can go through and those identified modes and see exactly, sort of like what Luca was saying. You see exactly, you don't have to create, any sort of modeling or anything. It's just immediately, and that's exactly what the object is doing. We can go through and look at some of the other ones here. Let's see here. You can see the vibration there, and then we'll do this 226. This is the one I wanted to show. So again, you can see these different modes. This one appears to be moving, kind of one side, or they're out of phase, where, the two sides are moving. Whereas, on this higher frequency, you have more of a bending across the entire disc, not just side to side. And so Luca mentioned with the phase map, it's kind of interesting because, again, all this data can be pulled back into motion amplification to kind of use that tool with it. And so what I want to show here in this is the phase map of this. So if you remember what this was doing, let's see, I can probably open up the, let's see. Well, that's all right. We'll just go straight to the phase map here. And so what this does is shows you what is in and out of phase with one another. The wheel here goes from 0 to 360. So things opposite on the wheel in color are going to be 180 degrees out of phase. Things that go from, from like yellow to red are going to be 90 degrees out of phase. And if you remember, we looked at this sort of 300, and you can see the pattern there, where you can see that it's not just side to side, it's sort of like quadrants, right? That mode shape is sort of like quadrants where there is, these areas are in phase and these areas are out of phase with one another. So opposites are in phase here, but the neighboring, sort of quadrant is out of phase. And then of course we can go to this 200 and see that, be a little slow. There we go. And see that side to side where it is in fact, sort of one side and the other are out of phase. So we've got yellow kind of to purple. So you can, the phase map is a very powerful tool to be able to leverage with this, to be able to see, not only, what's in phase, what's out of phase, but you can, to that point that Luca was bringing up, where your nodes and antinodes are, that you're, on a node, you're not going to see any vibration. And so, if you place a sensor there, you may not think there's any vibration. But, of course, that would be maybe for this frequency, it would be sort of on this slice, because you can actually see the transition from one phase angle to another phase angle.
Sorry to interrupt you, Jeff. Now imagine that you have done your simulation. Okay, you bump it and you can immediately overlap those colors to the color that you for sure have made in your simulation. Okay, and so you can immediately see, oh, it was right, it was wrong. Oh, it was wrong, why it was wrong. And quickly solved or quickly understood by everybody in the team. And
yeah, exactly. And that's another good point, with the communication, being able to explain it, very easily, very quickly. And again, don't forget that this is done in minutes. So you get these results, you'll get these results pretty quickly. And then if we go back to the, I mentioned the coherence map, I can kind of show that here. Let's see if this has already been done. Might do, yeah. So you can kind of see the coherence map at the, so for the different frequencies, you can see where the coherence is the strongest. In other words, you can see what areas of the object are actually being affected, their motions are actually are coherent with the input. In other words, that input from that strike is related. It has a strong coherence to the motion that are occurring at these locations. And you can so that's sort of an interesting new, ability with this technology to do a coherence map, much like we have our frequency maps and our phase maps. So you have frequency map, phase map, coherence map, which is interesting in and of itself. Okay, so let me open up one more example before we just kind of wrap up here. We'll do some questions. I have another example, which is, let's see here. Let me pull this off here. Open up recent projects. That's what I want. Let's see. Okay, here we go. So this is a blower, and this is the exhaust from it. And so this might be that, this would be interesting for modal analysis in that, you want to know what operating frequencies you can run. You certainly don't want to hit a resonance, condition in this where you really excite this. So let me show you again. We go immediately to the stability diagram. We get these frequencies. We can immediately see the mode shapes that they're there. Again, all these virtual measurements just done all the way around, simply all the way around this blower exhaust. And then we can do the analysis and immediately look at the the vibration. Again, we did higher frequency here. And let's look at, say, the 366. And we'll ramp this up. And get to a little higher. Put it back. And you can see this deformation mode shape, sort of around it. This is a little bit more classic example in the sense that it's, sort of like a, circular pattern. But you can see all these, and you can see them. And so, the different modes. And then I'm going to bring this over into phase map, so you can see it over in the with the phase. So we'll open that up. Phase map, and let's bring this over. We'll pause this. And let's look at the phase map here. Let's see. Okay, so there you go. So you can see, sort of this interesting pattern where you can immediately see. I like this because it's almost a rainbow effect where you're seeing all, lots of different phases all the way around. You can see this basically rippling effect where it's, the different areas, and you can see easily see where the change in the phase happens between these different locations. And it helps you visualize and understand the object that you're looking at, very, very quickly and very easily in terms of its behavior. So I just wanted to show a couple more examples of that. We're right at 10 minutes left. So I'm going to stop here. I'm going to go back to our presentation and just say that before we go, I always want to just kind of talk a little bit about some other things. These are some of our more recent products that you may or may not be aware of. We have launched a 3D version. That's what makes the Modal 3D capable with stereoscopic camera. We've also recently launched the Iris Explorer that's a spot payload for Boston Dynamics robot. Allows autonomous data collection and route-based vibration data collection with the camera. And then, of course, our Traveler, which is a more compact form of the Iris M that has zoom lens, single zoom lens, portable light, all goes in this small duffel, and you can carry it around without any components. It has some lights in there. So it's actually a very, very compact and easy to move around kit. And then just a little bit about, here's our spot payload. We'll just kind of show the very beginning of this video. But this is fully autonomous, and it's pretty amazing seeing it work. But it will go through, collect the data, and automatically collect that data, and then automatically find it. Does it if it walks to a new to the location. Maybe it's a foot to the right or left. It actually will find the same locations that it measured previous and make the data, make the measurement, historize the data, store it, trend it, all that kind of stuff that you'd expect from route-based vibration collection. And then also just to say that, we also do thermal. We can also use the camera to do thermal growth measurements. Just want to kind of point that out. This is over an hour and a half. So you can do thermal growth. Most people think of vibration and motion, on quick time scales, but you can really use any time scale, fast or slow. And in this case, this would be a slow time scale between measurements. And then finally, I just wanted to show this tack sync mode that I want to make sure everybody's aware of, because not everybody is. I continually, sort of run into people who are not aware that you can synchronize a tack to this and remove the synchronous motion. That is turning at 49 hertz. That tire coupling is, and this is actually spinning right there in that data collection. We remove the synchronous motion so you can see the non-synchronous motion. And this is really the only way that, way you can be able to visualize and measure, a shaft like this with the actual motion. So that removes the synchronous, and it sort of gets interesting because you can do fan blades and you can see torsion on a coupling. Here's a drone. This is one of my favorites, where we're going to do the top left, and you can filter the data as well. So there's one frequency of motion that is occurring that is non-synchronous, and then there's a second one, all from the same data collection. all from the same data collection. Okay, so that said, our next webinar is going to be March 30th at 1 p.m. If you're interested, it's going to be focused on industry focused on oil and gas. And then, of course, you can learn more. You can fill out a form, go to contact, or send an email to contact. There's my information. Connect with me on LinkedIn. You know, if you're active on LinkedIn, go ahead right now and just connect with me. I really enjoy seeing what other people are doing and keeping up with, sort of the industry. And then that's a QR code. You can scan it with your phone right now. If you have a question, if you want a demo, if you're saying, hey, I'd like a one-on-one demo of this modal, talk about my specific application and will it work for me? Scan that, submit it, and we'll get right back to you, within the next 24 hours or so, and we'll get you something set up to where we can chat with you one-on-one. So anyway, with that, we can stop, and we've got a few some time for some questions.
Yes, awesome, great. So one of the questions, thanks for the oil and gas plug there, because our next question kind of relates. So John wants to know how well this would work on a span of pipe offshore that might be challenging to view in one go. That's one part. And then can larger hammers be used on larger structures? Yes,
absolutely. So there's no real, the hammer just needs to be an IEP hammer. Then you put the sensitivity in there. So, you can use larger hammers for sure. Motion amplification works very well on pipes. In fact, I think that this is for piping. I think it would be my go-to technology for it. I know there's lots of other technologies, but for piping, it's large. The native unit for its tolerances are in displacement. It's often non-ferrous. It's often covered. So it's hard to monitor piping. Certainly motion amplification is very geared towards piping. And there's no reason why you cannot do, sort of a modal. It's really about impacting it properly and then getting the results. But for a very large span, it's a perfect fit for piping, in my opinion. I don't know if Luca, if you've got any.
I confirm 100%. Just need a larger hammer. Do it in the right way. Try to find the best position, and it works. I don't want to say 100%, but 90% it works.
Yeah.
Great, thank you. Nick wants to know, have you used this for determining high-speed belt tension?
High-speed belt tension. Okay. Yeah, I don't know. We don't have anything built in to automatically measure tension. Certainly you can pull frequencies from belts, but we don't have anything built in for the tension itself. Now, that said, you can do some interesting things with belts. For example, with motion amplification, you can do you can look at a series of belts, like, if you have multiple belts, and you can actually see that they're under different frequency, which tells you they're under different tensions, which tells you they're not all tensioned properly. I've certainly done that, and I've seen our customers use the technology in that manner. But there's not a, sort of like, draw an ROI on a belt and then measure the tension automatically. You probably have to do that through a calculator if you wanted, but you could get the frequency of the belt if it was vibrating, for sure.
Just add that normally the laser tension meter, they work with frequency. They give you the frequency, and then you have to calculate the tension starting from the frequency. So if you bump a belt, you're exactly doing the same. So it works.
Yeah.
Cool. All right. There's a couple questions, Jeff, on, we have an MA system, how do I purchase this system? What do I need?
Good question.
Yeah.
Yeah. So good question. So it's an add-on to an Iris M. It's plug and play with it. So everything comes in the kit, to just add right on. So it's just a simple add-on to the Iris M. So you would add the modal amplified and to your Iris M kit, and you're ready to go. Of course, if you want to do high speed, you put in an MX, you could add an MX, and if you want to do it in stereo, you could add the stereo camera. So everything's sort of modular. It's just you can build the system that you need. But if you're just going straight out for getting going and started with modal, you could just add the modal amplified kit to the iris in.
Okay.
Only one thing at the moment, it doesn't work with batteries. So you need a power cord.
Yeah, that's a good point. So you could go one of two routes. It is a plug, just like a normal, depending on your region, normal plug. I know there's a group that uses you can get sort of the power supplies that allow you to plug into it. So that would be an option if you had to go battery powered. Sort of use one of the, there's a lot of companies that make them for industry or for camping. These sort of plug-in kind of power generators that are really just batteries. But yeah, it's a good point. We're looking at adding battery capability in the future for the.
I was trying to bump my car, and the goal was to put it outdoor, and then I realized the cable was not long enough.
Yeah. It is ultimately DC powered, so we'll probably add a battery, get to where the DC terminal can come out, so we can battery power it.
Well, thank you both. We are at the top. It's 1:59. We have one last question, Jeff, and I think we answered this a little bit, but they're asking, can we do an in-person demonstration of the equipment? They would love to implement the technology out in Montana. The naysayers, they feel if they see this in person that it just dissolves all that. So any feedback there?
Yeah, I would say reach out, scan the QR code, reach out, we'll get something set up. I think that's not a, that's certainly we can help you, get that accomplished. We do that all the time, and we've got ways to do that. We've got people, all across the US, to be able to come on site and that sort of thing. And it is very true. We use the seeing is believing, and that's about using the product, but also seeing the technology in action is very powerful for the people who are skeptical, and so that's not uncommon. And we're glad to healthy skepticism is good, and we're glad to dispel that and kind of show that it really does what it says it can do.
Great, thank you.
Switzerland, again, we are available for demonstration if someone is listening from Italy or Switzerland as well. Yeah,
and I just, as we're wrapping, I just want to thank Luca for joining us. We do these webinars, and I've done lots of them, but there's nothing better than having practitioners on that sort of have, Luca's been in the industry for many years, and sort of an expert in this domain, and so to have him come on board is very, very nice, and we're very appreciative of his time.
It's been an honor and a pleasure.
Thanks, everybody.